All right. So it is May 14. We are moving fast. We're in week 7. We got one more section here and then 2 more chapters, and then we are done with the term. So 5.5 is all about logarithms. I'm going to talk about that a bit today, and then you'll definitely get through it. We have plenty of time. Wednesday, we start kind of combining functions. We did a little bit of changing general functions when we did transformations, moving them side to side, up and down. We're going to look at other ways to change functions. We're going to get 2 functions and add them together, or subtract one from the other. We're going to take one function, we're going to do something to it. We're going to take that same thing, do something else to that, right? A composition. We're going to take a function, go forward. We're going to take a different function, go right back to where we started. 6.1, arithmetic with functions. 6.2, composing functions one after the other. 6.3, inverting functions, going forward and backward. Now, I will not be here on Friday 6.2 or Monday 6.3. Dr. Murat Cole will be here. Dr. Cole is great. And also, I know you're used to the way I introduce material. So what I'm going to do is I'm going to do mini lectures that will be posted by Thursday on section 6.2 and 6.3. So when you come in, you'll get the same thing that I would do if I were up here. And then Dr. Cole and the learning assistants will assist on Friday, and Dr. Cole and everybody will assist on Tuesday. No midterm this week. We have a wrap-up 7, which covers chapter 5. That will be a correct grade scope assignment. You got some homeworks coming up at the end of the week and the beginning of next week, and then a week from Thursday, you have your next quiz. And it's been a while. Chapter 4 and 5 will have gone, well over a week for even chapter 5, and 4 weeks back for chapter 4.1. So we're going to budget some time for a review session on Wednesday, the 22nd. I'll put some review questions online. I should make notes. Wrap up 5 grade scope review cues for 4 and 5. We'll either budget some time to do that, or I might actually do that on Tuesday. I have Dr. Cole and everybody just lead a review session the way we did that other Tuesday. I want to do that. I'll change the calendar. You don't have to be able to read this. Those are for me. Okay, so I'll get an updated calendar. I'll check in with all of you sometime. We'll make a plan. I'll put review questions online. Then you can all go through them on Tuesday. Whatever format Camden, you and Dr. Cole come up with is fine. We'll get through 7.1 on that Friday, and we'll move 6.3 to that Wednesday. Yeah, that's what we'll do. I like it. Okay. Any questions about our calendar? Yeah. And Alex, what? Yes, that's exactly what I'm going to do. Either that or one I write myself. Yeah. But yeah, there will be a series of questions, roughly 20 questions for review. Yeah. Yeah, and videos. Okay. Good question. Any other questions? Yeah. Once everybody who's taken it has taken it, and I'll check today. I had to give a couple people a little bit extra time, which is fine, but yes, we will. Yeah. Thank you. Okay. Other questions? All right. Let's talk about logarithms. I feel like this is fuzzy. That's better. Okay. All right. So this is section 5.5 in the book. We are really most of the way through it. We've got this table that has the property of logarithms. I will go through this. This part of the table will be on your quiz, and you will be asked to use it on your quiz. But that's not the most important thing about logarithms as far as I'm concerned. So I want to talk about what logarithms are / what do they do. Okay, I'm going to turn that off now because that's bothering me. Logarithms. What are logarithms? And what do they do? Anybody ever seen Kindergarten Cop? Who is your daddy and what does he do, right? Yeah, you're there. So, yeah, I've seen twins a long time ago. All right, so logarithms are inverse functions for exponentials. If an exponential function goes this way, a logarithm goes that way. That's the first thing I want you to keep in mind. How do exponential functions work? Like, what's their basic? They grow and they shrink through what type of arithmetic? Multiplication, exactly. So logarithms are inverse functions for exponentials. They undo exponential functions. And what's interesting about them, and the reason I started with comparing linear functions to exponential functions, I'm going to write not the full table, but I'm going to write part of it again. Here's linear. Here's exponential. And in the exponential world, I can't spell today. Multiplication. What's the linear analog of exponential multiplication? Addition. And to get there, you take a log. And you get addition. Logs turn multiplication into what? Addition. What about division? If you take a log, what do you get? Subtraction, exactly. Logs turn division into subtraction. They turn powers into, check your notes if you want, take a minute. They turn powers into multiplication. Multiplication. And they turn roots into division, exactly. They simplify the arithmetic operation. If I have y equals c times a to the x, and I take a log, I always like to use natural log because it really doesn't matter what base you use. In the end, everything grows like the natural exponential. So I use natural log, so I'm going to use ln right there. What you get is the natural log of y equals the natural log of a times x plus the natural log of c. What's the arithmetic between c and a right here? And when I take the log, it turns into addition. What's the relationship between a and x right here? And when I take the log, it turns into multiplication. So this is just a funky way of saying y equals mx plus b, only it's not y, it's the log of y. It's a little different, right? But it took an exponential with multiplication and powers and turned it into a linear with addition and multiplication. This is super powerful because how do things usually grow? Do things biological systems, do they grow linear or exponential? Exponential, but exponential things are hard to work with. What are easier to work with, linear or exponential? Linear, so we use a log and we make exponential things linear, and that makes our life a lot easier. Computers, do they work exponentially? They don't. They work through ones and zeros, specifically addition. But how do you think computers handle exponentials? They do logs, yeah. All right. So a log turns multiplication into addition. It turns exponentials into linears, right? Because it undoes what the exponential function does. It's an inverse. If you take a log of an exponential, you get a multiplication, you get addition. You take a log of division, you get subtraction. You take log of powers, you get multiplication. Take log of roots, you get division. And if you take a log of an exponential function, you end up with a linear function. So now let's go over to page 138 and look at our properties of logs. And I think what you're going to see is this is just a fancy way of saying what we just said. I'm sorry, it's not super focused. Try it again. Stop. Okay. Log base A, we're going to get into what all this stuff means in a minute, but what kind of operation is happening between, it doesn't even say, M and N are two numbers. A is a number, okay? What's the operation between M and M right there? Multiplication, and when I take a log, what does it turn into? Addition. So for example, I'm still going to use ln, and sometimes I use it just because there's less writing. E times 7 is a natural log of 3 plus the natural log of 7. That's not 3. Logs turn division into subtraction. Log of 5 divided by 8 equals log of 5 minus log of 8. Logs turn powers into multiplication. There's a multiplication right there. Natural log of 3 to the x is x times the natural log of 3. The one-to-one property, this means it's an inverse. Log is an inverse function. And I know graduate students, you're going to complain that I'm not using the precise language, but good enough for me. If I have two numbers and the logs are the same, then those numbers are the same. It seems really obvious. If I tell you that log of x equals log of 10, what does x have to equal? 10, right. Super obvious. Don't even think about it. Let's do another one. If I tell you that x squared is 16, you can't see that, then x has to equal or -4. If I know that x squared is 16, I don't know what x equals. But if I know the log of something is equal to the log of x, then I know that thing is equal to x. Right? So this is not something that comes with all functions. It only comes with invertible functions. So it's actually a really powerful property. We're going to talk about these in a minute because and you had a little bit of practice with this at the beginning when we talked about logs. So let's have a little more practice with it now. Everybody has maybe a different way of thinking about logs. One way I like to do it is to use different representations of functions. There are formula representations like this. There are graphical representations like this. There are table representations like This. It tells you information about the function. But they're also verbal representations. And so I find for students who are like, I got this, I'm good, that's great. For students who are struggling, I really recommend going through the verbal representation whenever you switch from a log to an exponential. So if I said 7 cubed equals 343, do you agree with that? Yeah, you did the right thing. Pull out your calculator, Fizz, and just try it. Yeah, do you agree with that? Is this right? I might be wrong. It's not right? Okay, well, you can check and test and make sure. Sorry, I'm gonna drink of water. It is, it's 343. We're okay. Here's the verbal representation. 3 is the power that goes on 7 to get 343. Would you agree that this is the English sentence that represents that expression? Yeah. So a log just writes this sentence in a different way. 3 is the power. Whenever you see the word is in mathematics, what is the word is? What symbol do we use to represent the word is? 2 times 6 is 12, equal sign. 3 equals the power that goes, here, let me change this. I circled too much. That's a the, is that, yeah. Okay, so 3, that's pretty obvious. Boop, boop, is right there. The power that goes on, the power, this is the word log. So if you want to think about a log, it's a power. It's a power that goes on a number. Why do we call it log instead of POW? I don't know. Probably German. Nothing wrong with that. It's just, you know, it'd be easy if we used, like if we literally called it POW, it would be a lot easier to remember, but we don't. It goes on 7. So there we go. We put it right on 7, right? It's sitting on 7. To get goes on 7. That goes here. To get 343. And now we have written this expression like an exponential. We have written it with words, and we have written it with a log function. Let's do one more, and this time I'm going to get you to do it. By the way, if you're practicing, don't ever use the number 2. 2 is the power that goes on 2 to get, right? That's terrible. Too many 2s. I learned that early on. Little pro tip for all you. Don't do logs with the number 2. It's terrible. All right, but let's look at 5 to the 4th. That's equal to 625. Can someone read that as a sentence in the same way as this one? Get a volunteer, maybe someone who, oh yes, perfect. Yeah, 4 is a power. It goes on 5 to get 625. Okay, if you didn't get that, that's okay. That's why we're here, we're learning. Now write this as a logarithm expression, as a logarithm equation, and then we'll check work. Take a minute. You're killing me with that sandwich. I'm so hungry. Can I have some of your sandwich? I'm kidding. I have my own. I have my, All right. What was your name again? What was your name again? Okay. F for Ethan. My kid's name is Ethan, so you're in the clear. But if we're Damien, who's my nephew, you'd be in trouble. All right. 4 is the power. 4 is, that's easy, the power. There it is. I wrote it in German. Does anyone speak German? Is power German anything to do with logarithm? Okay, let's pretend it is. Let's say it's ancient German. Latin. Latin. Does anyone speak Latin? I didn't think so. Okay, so there it is in Latin. Thank you. Updating my knowledge. Thank you, Camden. That's the power. It goes on 5, so we just put it right on 5. See, it's sitting on there to get 625. Okay. Let's practice one more. Write that one as a sentence, like as a verbal representation. What is that telling you? No, did I write that backwards? I wrote it backwards. Don't write that one. That wouldn't have been right. That's correct. Little tip, write the number first and then write the log. Not everything in mathematics comes from German or Latin, but an awful lot of it does. Some comes from French. Somebody else want to read this sentence to me? Yeah. Yep. And you see why that was wrong? If we had tried to do it that way, it would have been wrong, right? 81 is not the power that goes on 3 to get 4. That's definitely not right. 4 is a power that goes on 3 to get 81. Okay. So 4 is the power that goes on 3. 4 goes as a power on 3, and it gets you 81. There we go. All right, this will be up here if you want to take a look at it, but I want to keep on trucking. So let's go back to page 138. And let's look at these power rules, first power rule and 0 exponent rule. Let's write this, try to write this underneath as that statement. Something is something that something on some, right? Try to write that as a statement and see if it makes sense to you. Using that. Sorry, I can't show them both at the same time and also be zoomed in. Something is all right. What goes in this first one? First blank. 1 is the power that goes on A, that's this little a, to get that a. Do you all agree that if I put 1 as the power on A, I get A? 1 is the power that goes on the base A to get this A. Yeah, so 3 to the first equals 3. Or log base 3 of 3 equals 1. These are equivalent statements. Try it with the next one. Try it with the log base A of 1 equals 0. Which one of these is do we write down first? The 0, the 1, or the A? 0 is the power that goes on A to get 1. A to the 0 equals 1. Do you agree with that? Any number to the 0. So this statement is exactly the same as that statement. So I could say 5 to the 0 equals 1, or log base 5 of 1 equals 0. Those are equivalent statements. At this point in the program, you might go back to your level of confusion when you were thinking about, well, what's log of 0? Because now you're thinking about where all of these numbers go. What is log of 0 for any base? Log of 0. What is log of 0? It's the power that goes on, let's say 7 to get 0. What power can you put on 7 and get 0? 7 to 0 is 1, right? So this is undefined. So this one in particular, these two things are going to be confusing for a little while, and that's okay. Just remind yourself, maybe make a flashcard, flip a coin, right? So that you remember which one represents which. Okay. Last thing I'm going to say, then I'm going to turn you loose. So a lot of what you're doing today is just using these properties. We don't care what log base 3 of 30 or log base 3 of 70 is. We don't care what that decimal number is. Actually, that is the number. It's just written in Latin instead of all in numerals, right? It's just got a little bit of Latin in there. So we don't care to get a decimal approximation for this right now. We just want to know that if I have log base 3 of a number and I add it to log base 3 of 10 and I get log base 3 of 70, I should be able to figure out what this number is. It's not the number 0. So now I'll turn you loose. I'm going to refill my water and I'll be back. Stop recording.